up until March 15th, 2026. Interacting with AI was, well, it was basically like owning a really smart golden retriever.
Yeah, that's a good way to put it.
You throw a prompt, it fetches an answer. It was just entirely passive.
Right, totally passive.
But over the last 7 days at the GCC 2026 conference, NVIDIA didn't just announce faster chips. I mean, they essentially handed the dog the keys to the car. We have officially crossed the threshold into the agentic era.
We really have. And that shift from passive generation to active autonomy, it just changes the entire computing paradigm. I mean, we are no longer dealing with systems that just output text or generate images.
No, not at all.
These are autonomous agents now. They are capable of long-term planning, executing raw code, retrieving their own data, and, interacting directly with other digital systems in real time without any human intervention.
It's honestly staggering. And the sheer volume of hardware and software announced to support that shift this week has been massive. So, our mission for you today in this deep dive is to cut straight through the noise of this huge product dump.
Yeah, there is a lot to cover.
Exactly. We are focusing exclusively on the factual updates published globally between March 15th and March 21st. We're decoding how new mathematical frameworks, operating systems, rack-scale hardware, and enterprise deployments are all structurally connected to make these autonomous agents a reality. So, okay, let's unpack this.
Well, if we want to understand how an AI agent can act autonomously in the real world, we have to look at the foundational mathematics first.
Right.
Because before an agent is allowed to, say, book a complex travel itinerary or synthesize a pharmaceutical drug, the underlying open source models driving its reasoning have to be rock solid. And that is exactly where NVIDIA's research division focused its initial global announcements.
Which takes us to the March 16th global dispatch from the NVIDIA newsroom.
Yeah.
The headline is the Nemotron Coalition. What happened is NVIDIA formed a formal partnership with 8 leading AI labs, and this includes Mistral AI, Perplexity, and Cursor. They are pooling their data and compute to co-develop open frontier models, starting with the Nemotron 4 base model, which is being trained right now on DGX Cloud.
And why this matters fundamentally is the democratization of agentic building blocks. Historically, the most capable foundation models, the frontier models, they've been heavily guarded by a few massive monopolies.
Right, closed doors.
Exactly. But this is NVIDIA's first open AI mega project. By decentralizing the development of Nemotron 4, they are ensuring that the core reasoning engines of the agentic era aren't controlled by a single corporate entity. It gives developers globally a standardized open source brain to build upon.
But dropping a massive open source brain into a dynamic environment, that introduces some serious reliability issues, right?
Oh, absolutely. It really does.
Which brings us to a highly technical but critical paper published on March 16th globally by NVIDIA research out of Tel Aviv. They presented at the AI Stats 2026 conference. The headline is Reliable Policy Iteration, or RPI, and Conservative RPI.
Yes, this one is huge.
What happened is researchers formulated a way to restore tabular guarantees under function approximation in deep reinforcement learning.
Right, and for anyone building autonomous systems, this solves a massive mathematical headache.
How so?
Well, in deep reinforcement learning, an agent learns to achieve long-term goals by mapping its environment. But real-world environments are just too complex to map perfectly.
Too many variables.
Exactly. So the system uses neural networks to approximate the state of the world, and that's function approximation. The problem is, this approximation inherently introduces compounding errors. The agent's mathematical value estimates become unstable or non-monotonic.
Okay, wait.
Basically, its internal compass for what constitutes a good or bad decision gets completely scrambled.
Let me make sure I'm getting this. Is this essentially like a GPS navigation system that works perfectly 99% of the time, but because of a slight map rendering glitch, it suddenly hallucinates a bridge over a canyon that doesn't actually exist?
Precisely. That's a great way to look at it. The neural network is estimating the terrain, and a compounding error might convince the autonomous agent that accelerating over an empty gorge is the optimal route to the destination.
Wow.
Yeah. So what the Tel Aviv team achieved with RPI is a mathematical failsafe. It acts as a strict guardrail, guaranteeing that the agent's policy will only ever improve or stay the same. That's monotonic improvement.
Got it.
It forces the system to recognize its own uncertainty and literally prevents the AI from driving off the cliff during complex multi-step planning.
Applying that flawless reasoning to physical architecture is where we see immediate real-world value. Looking at another global announcement from NVIDIA Research on March 16th, this one co-developed with Google DeepMind, the headline is the Proteina-Complexa model.
Right, the biomolecular one.
Yeah. What happened is researchers utilized latent generative search to predict entirely new, de novo biomolecular interactions.
And why this matters is just the sheer scale of the output. I mean, they successfully expanded the AlphaFold database by 30 million predictions.
30 million.
30 million. And that includes 1.7 million high-confidence protein complexes. Latent generative search isn't just matching existing puzzle pieces. It is navigating a vast mathematical space of possible 3D molecular structures to find novel ways proteins can bind together at the atomic level.
That's incredible.
It really is. It vastly accelerates the initial phases of drug discovery from years down to mere weeks.
But having mathematically flawless models in a research lab doesn't really help a developer trying to deploy them in Silicon Valley. I mean, if you drop thousands of these self-evolving agents onto a standard corporate server, the infrastructure will bottleneck almost immediately.
Oh, instantly. It would crash.
You need a dedicated traffic controller. So on March 16th, a global release from the NVIDIA newsroom announced Dynamo 1.0 Inference OS. What happened is NVIDIA released a production-grade, open-source distributed operating system specifically designed for AI factories to orchestrate GPU and memory resources.
Yeah, and the operative concept here is disaggregated inference.
Right.
When you have thousands of autonomous agents querying a system, they demand highly variable amounts of compute and memory at completely unpredictable intervals. Dynamo 1.0 manages this chaos right at the infrastructure layer.
How does it do that?
A prime example is KV cache management. The key value cache is essentially the AI's short-term working memory, storing the context of an ongoing interaction. As context windows stretch into millions of tokens, that memory footprint becomes massive.
Let me introduce an analogy here to visualize this.
Yeah.
Is disaggregated inference like a highly efficient expediter in a busy restaurant kitchen?
Okay.
Like, instead of one chef trying to make a complex dish from start to finish and just running out of counter space, the expediter seamlessly moves the ingredients, the data between the prep station, the grill, and the garnish station without dropping a single plate.
That fits perfectly. Dynamo 1.0 is paging that massive KV cache memory across the NVLink network, distributing it across multiple GPUs so no single chip runs out of VRAM. It physically manages the GPU to GPU data movement.
Oh, wow.
Yeah, and because it streamlines this at the lowest possible operating system level, it delivers a 7x inference throughput boost on NVIDIA's Blackwell architectures.
Okay, so traffic control handles the speed, but security is an entirely different beast when dealing with autonomous systems. Also out of the NVIDIA newsroom globally on March 16th, the headline is NemoClaw and OpenShell.
Right, the security stack.
Exactly. What happened is NVIDIA launched a reference stack and runtime environment to secure the deployment of OpenClaw autonomous agents. They are specifically utilizing Linux kernel isolation tools like seccomp and landlock.
And why this matters is it transitions AI cybersecurity away from brittle application layer prompts. Up to this point, developers have essentially just typed instructions telling the AI not to do malicious things.
Which doesn't always work.
Right, prompts are easily jailbroken. But OpenShell moves the security down to the foundational infrastructure layer. Tools like seccomp, which stands for Secure Computing Mode, literally strip away the AI process's permissions to execute system calls.
So it can't even try.
Exactly. If an agent goes rogue and tries to delete a database or open an unauthorized network port, the Linux kernel instantly kills the process. It's mathematically verified containment, so enterprises can deploy self-evolving agents without risking a systemic network breach.
I have to push back on the framing of OpenShell, though. I mean, I see the distinction between cognitive freedom and physical restriction. But practically speaking, if an agent is truly autonomous and discovers a novel, highly efficient way to solve a problem that requires accessing a lockdown network, isn't it going to just hit a wall? Doesn't this containment defeat the purpose of autonomy?
It absolutely hits a wall, but in enterprise deployment, that is a feature, not a bug.
A feature?
Yeah. You want the agent's brain to have the cognitive autonomy to devise that novel solution, but you do not want its hands to execute an unauthorized network breach to achieve it.
Ah, I see.
When the agent hits that kernel-level wall in OpenShell, it is forced to either find an authorized path or flag a human administrator for permission. It restricts the blast radius of the agent's actions without stunting its logical reasoning.
Limit the hands, free the brain. Like that.
Mhm.
And speaking of freeing up computational resources, we have to look at the visual limits of this technology. March 16th, global release from the NVIDIA newsroom. The headline is DLSS 5 Neural Shading.
This one is super interesting.
Yeah. What happened is NVIDIA announced software that blends traditional 3D rendering with generative AI to predict and fill in visual details in real time.
They are dubbing this the GPT moment for graphics. And the reason it matters is the massive reduction in computational load. In traditional rasterization, the system calculates light bounces in geometry for every single pixel on a 4K display.
Which takes a ton of power.
Exactly. But DLSS 5 renders a lower resolution base, and the generative AI instantaneously hallucinates the high-resolution, photorealistic details. It frees up enormous amounts of GPU compute. And that's critical not just for gaming, but for rendering complex 3D digital twins of real-world factories and cities.
Which brings us to a harsh physical reality. Running Dynamo 1.0, managing thousands of sandboxed agents in OpenShell, and generating neural graphics simultaneously that completely shatters the limits of traditional hardware.
Oh, completely.
To make this ecosystem function, NVIDIA had to stop thinking about individual chips and redesign the data center at the rack scale. So looking at the global March 16th NVIDIA newsroom dispatch, the headline is the Vera Rubin platform and Vera CPU.
The new supercomputer.
Right. What happened is NVIDIA unveiled a next-generation AI supercomputer integrating 7 newly co-designed chips. This features the Rubin GPU with HBM4 memory and the new Vera CPU with 88 ARM-compatible Olympus cores.
And the defining architectural shift here is the liquid-cooled NVL72 rack. They are no longer treating a server rack as a collection of separate computers wired together.
It's all one unit now.
Exactly. The entire copper backplaned rack functions as a single computing node. By co-designing the CTU, the GPU, the networking, and the memory to act as one cohesive organism, the platform achieves up to 10x higher inference throughput per watt.
10x, that's massive.
It is. And more importantly for the industry, it does this at 1/10 the cost per token compared to the Blackwell generation.
Okay, here's where it gets really interesting. March 16th, global release from the NVIDIA developer blog. The headline is the Groq 3 LPX integration. What happened is the Groq 3 language processing unit, which is technology originating from NVIDIA's recent $20 billion asset acquisition, was integrated directly into the Vera Rubin platform. And it specifically utilizes on-chip SRAM instead of traditional high-bandwidth memory.
And why this matters requires looking at the physics of memory. High bandwidth memory, or HBM, has massive capacity, which is strictly necessary for training trillion parameter models. But retrieving data from HBM introduces microseconds of latency. SRAM, on the other hand, sits directly on the processing chip.
Let's ground that. Is using SRAM instead of HBM essentially like a chef keeping all their critical ingredients chopped and ready right on the cutting board, instead of constantly having to walk across a massive kitchen to pull items out of a walk-in freezer?
Exactly. The walk-in freezer holds vastly more data, but the walk takes time. The SRAM cutting board holds less, but access is functionally instantaneous.
Makes sense.
Because agentic AI requires constant back-and-forth interaction. Retrieving tools, parsing logic, and executing code token by token ultra-low latency decode is non-negotiable. Integrating Groq's SRAM architecture delivers up to 35x higher inference throughput per megawatt for these complex models.
And they are taking that exact low-latency compute to extreme environments. March 16th, NVIDIA Newsroom Global Announcement. The headline is Space One Vera Rubin. What happened is NVIDIA announced initiatives to bring AI compute to orbital data centers.
Space.
Yes, space.
And why this matters is bandwidth. Satellites generate petabytes of geospatial and optical data. Beaming that raw data back down to Earth for processing causes massive latency.
Right, it takes too long.
Exactly. So the Space One platform is ruggedized to withstand zero gravity and high radiation, delivering 25x more AI compute than the H100 chip directly in orbit. It allows the satellite to process the data locally and beam down only the actionable insights, effectively extending the edge of the computing network into space.
Now, with hardware capable of operating from orbital data centers down to the kernel level of corporate servers, it's inevitable that governments step in.
Oh, of course.
And just to be clear for the listener, we are strictly looking at the facts of these regulatory actions without taking any sides. We're just reporting the filings.
We're just looking at the legal mechanics here.
Exactly. So looking at the geopolitical and regulatory landscape, we have two major developments. March 19th, based in the U.S., reported via Bloomberg and U.S. Congress records. The headline is the antitrust investigation into the NVIDIA Groq acquisition. What happened is U.S. Senators Elizabeth Warren and Richard Blumenthal sent a letter probing the $20 billion Groq licensing and asset acquisition deal to determine if it bypassed standard merger review.
Why this matters is it represents the first major regulatory scrutiny of an NVIDIA deal of this scale, and it highlights a massive gray area in antitrust law. When a corporation executes a traditional merger, buying the competitor's stock, it automatically triggers regulatory review by bodies like the FTC or DOJ under the Hart-Scott-Rodino Act.
So why is the structure of an acqui-hire or an asset purchase treated so differently?
Well, because technically the original company isn't being acquired. In an acqui-hire structure, the larger corporation hires all the top engineering talent and licenses the exclusive rights to the intellectual property.
But the company still exists.
Legally, yes. The original company still exists, it's just an empty shell. Regulators are actively investigating whether this is a legitimate licensing strategy or a deliberate loophole designed to absorb competitors and consolidate market power without triggering those automatic antitrust thresholds. This probe could set a landmark legal precedent for the entire tech sector.
And we are also seeing immediate friction regarding the physical hardware itself. March 16th, out of the U.S. and globally, reported via the U.S. Department of Justice and CNET. The headline is the DOJ indictment of Supermicro executives.
Right.
What happened is an unsealed indictment charged 3 individuals affiliated with Supermicro Computer for conspiring to illegally export restricted NVIDIA AI servers to China via intermediary shell companies.
This underscores how these chips are classified today. They are no longer viewed merely as commercial enterprise hardware.
No, not at all.
They were heavily restricted strategic national assets subject to intense export controls. The fact that sophisticated multinational shell networks are allegedly being established to smuggle this specific hardware highlights the extreme geopolitical leverage and black market demand surrounding NVIDIA's infrastructure.
Despite the intense regulatory probes and the geopolitical smuggling operations, the enterprise sector is placing trillion-dollar bets on this infrastructure right now. March 19th, global announcement via the NVIDIA blog in Tech Republic. The headline is the AWS 1 million GPU deployment.
1 million.
Yes, 1 million. What happened is Amazon Web Services expanded its partnership to deploy the full Vera Rubin and Groq 3 computing stack across its global availability zones.
And why this matters is the unprecedented scale. A commitment of over 1 million GPUs represents the single largest public cloud deployment in history. AWS is effectively laying down the hyperscaler power grid required for mass-market agentic computing.
So what does this all mean for the listener? I mean, how does an AWS data center purchasing 1 million GPUs actually change the day-to-day experience of someone using an AI agent?
It completely eliminates the friction you experience today. Right now, if you ask an AI to handle a 20-step task, you watch a loading spinner, wait for the generation, and, frequently the system just times out.
Yeah, that happens all the time.
But when your personal agent is backed by 1 million GPUs operating on Dynamo OS with ultra-low latency SRAM chips, that processing lag vanishes. Your agent can search the web, execute code, and finalize bookings near instantaneously because it has an ocean of compute power resolving its logic in real time.
And we're already seeing that speed generate massive returns in healthcare.
Yeah.
March 16th, global release via the NVIDIA blog. The headline is Roche Scales AI Factories.
This one is fascinating.
What happened is pharmaceutical giant Roche and Genentech are deploying over 3,500 Blackwell GPUs across their global infrastructure for digital twins and lab automation. And why this matters is the return on investment. They've accelerated drug degrader projects by 25%, cutting research timelines from over 2 years down to just 7 months.
This is the realization of physical AI. I mean, we've moved far beyond chatbots. This infrastructure is mathematically simulating biological interactions to generate physical cures.
And it extends to physical mobility, too. March 15th, U.S. and global release on the NVIDIA blog. The headline is the Uber Robotaxi Fleet Partnership. What happened is Uber announced they will deploy autonomous robotaxis powered directly by NVIDIA's autonomous driving software. This is launching in LA and San Francisco in 2027, scaling to 28 cities by 2028.
Wow.
Yeah, and why this matters is it proves NVIDIA is moving beyond just supplying the silicon. They are validating their full-stack physical AI software on one of the largest ride-hailing networks on Earth.
It really demonstrates the complete vertical integration we've seen unfold this week, from the mathematical research all the way to vehicles operating on public roads.
It has been a monumental week to track. Just to recap the journey of this deep dive, we started with the Tel Aviv researchers mathematically fixing reinforcement learning to ensure agents don't hallucinate.
Right.
We explored OpenShell securely, sandboxing those agents at the Linux kernel level. We covered the Vera Rubin NVL72 racks and orbital data centers, completely rewriting the limits of hardware. And we concluded with AWS and Roche, proving this technology is actively reshaping the global economy.
You know, if we connect all of these developments, there is a really fascinating implication here.
What's that?
NVIDIA's CEO, Jensen Huang, stated this global infrastructure build-out will eventually reach $1 trillion. But as these AI factories scale into gigawatt operations, and as these agentic systems gain secure, self-evolving autonomy, it raises a profound question. Will the next generation of NVIDIA architecture, the silicon that comes after Vera Rubin and Feynman, be designed by human engineers? Or will it be engineered by the AI agents themselves, endlessly optimizing the physical hardware for their own efficiency and logic?
And intelligence designing its own superior housing. That is definitely a thought to sit with as this technology accelerates. Thank you for joining us for this deep dive into the agentic era. Keep questioning the rapid evolution of the systems around you, and we will see you next time.